So I'm looking forward to this because I always wanted to use them in F#, but we don't have them. The first talk is about type inference for generalized algebraic data types, and it's presented by Jacques Garrigue.
Okay, thank you. So this is about tracing ambiguity in GADT type inference. This is, you can see it as a sequel to what we did last year at ML Workshop 2011. I don't know how many of you were there. So I was asked, in case some people still don't know what GADTs are, a short primer. So generalized algebraic data types. They are basically the usual algebraic data types, but they are allow different type parameters for different cases. This is the simplest way to see it. So they are quite similar to inductive types in Coq, and we use actually the same syntax. So if you already know Coq or GADT in Haskell, it's exactly the same way. So here I'm just defining an expression types where my expressions actually are going to express what their content is. So if I have an integer, it takes an integer argument and returns an integer expression. Add is just a constant of types, it's an expression of type int to int. And application takes a function expression, an argument of the right type, and return an expression of the result type. This is just a data type. Now I can, of course, form terms with it. So if I do a partial application of add to 3, I get an int expression. So what's interesting about GADTs is that they're able to express invariants about data structures. They're also able to express proofs about your programs. All this directly inside your language. A side note is about this add constructor. Actually, when you start using GADTs, you actually quite immediately need existential types. So here, when a type variable doesn't appear in the result side of the constructor, it means that it's in existential type. So app actually takes it exists something where there exists some a such that I have an a to bx and an ax. Okay. So when I'm going to unpack this, I will have existential types. So here I've just given you the definition, but of course the interesting part is when you are going to analyze your values. Oh, of course they are in OpenNet 4.0. And the interesting aspect of GADT is pattern matching. The point being that when you match on a GADT constructor, this introduces local equations in the body of your pattern matching, which you can use to types morphics. In our system, the parameter must be a rigid type variable so that you can refine it. And on the other side, if you have existential, you will introduce fresh rigid type variables. Okay, so here is I follow on this example. So I define an eval function for my small language. Since I need the rigid type variable, I must be explicit about my type here. I have this syntax which says, oh, I have a type A, I introduce type A here, which is a, it's locally abstract types. And my function is from an AX to an A. And I go by case analysis. So if I pattern match an int, I will get the equation A equal int. So here I'm returning n, which is an int, but since I have the equation, it's compatible with A. Okay, the same thing since I add, the equation A is int to int, and I return, if I return plus, which is int to int, it has the right type. And for application, actually application is not really a GADT case, because the return type was just an A expression. But I need to introduce an existential variable here. So actually my f for some rigid b, f will be b to a and x will be b. So the only thing I can do is actually apply f to x. Actually x, that's the idea. And the other interesting here is that we need to use polymorphic recursion. So f of x are on different types, but I can use eval on both of them. So I get a function with expected types, and I can use it as expected. A slightly technical note concerned about how it's implemented in OCaml is that we are using those this I call rigid type variables were actually implemented at locally abstract type, something this was introduced in the previous version of OCaml for, in combination with first-class modules. The point is that for polymorphic recursion, actually we need something else which is universal type variables. So we end up with a new syntax which combines the two features. So when I write type A dot AX to A, as my example in the previous slide, actually it means I want polymorphic recursion, so eval is of type quote A dot quote AX to quote A, but I'm also introducing a locally abstract type. I'm forcing my expression to have this type. Okay? But in this talk, actually, we are talking about type inference, and we will not really deal with recursion in the example, so I will not use this syntactic trigger much, so we will more see about these type A things, which are really this one. There's no real distinction. Okay, what this talk is about. Well, first, GADT type inference is difficult. Actually, the way we did it last year was not really good. Traditional approach use explicit types, but we see problems with that. So our approach is a new idea, which is to use a refined notion of ambiguity detection, which allows you to type more programs and in a more regular way with better principality properties. And of course, we want also to compare it with what is probably now the state of the art in GADT type inference, which is GADT's outside-in algorithm. Okay. So GADT and type inference. Well, first aspect, providing solid type inference for GADT is not particularly difficult. I think everybody knows how to do that. What is difficult is that actually providing principal type inference for the unrestricted type system, where you allow to use all equations anywhere they are available, is just not possible, because you get this kind of ambiguous cases. Okay, here I have a very simple example. Just see my T has only one case, int, which provides, the idea is it's going to provide an equation A equal int. This is the only role of this constructor, constant constructor. So I write just this first program. I introduce my rigid type. I say that x has type AT. Now I match x on int. This introduce A equal int. Okay? And I return 1. 1 is of type int. So what happens? What should be the return type for this function? The problem is both int and A are valid choices. And they are not compatible. So such a situation is called ambiguous. And, well, we have to do something about that. So, the classical non-solution in this kind of situations is just be explicit. And if you are truly explicit, it means basically that on every GADT pattern matching, you must annotate. So you annotate both the subject of your pattern matching and the return type. So I say, okay, my pattern matching data x AT and returns an A. Okay, so this is actually the kind of syntax used in code, for instance. And then there is no longer any ambiguity. It's not that I'm returning an A, so it's even though one is int, it will be converted to A. And in practice, if we allow some propagation of annotation, this doesn't sound too painful. For instance, here in top-level function, and the idea with GADT is you give their types. It's a good idea anyway, because you need to express what you want. And if I give this type, I can propagate, say that this one should be, the argument to the function should be AT, and the result should be A. And this result actually what I have on the upper side of the slide. Okay?
But that's not really a solution, because there are variables in the environment.
That's next slide. Is it really sufficient? No, of course. As you say, there are variables in the environment. Here I introduce, I have a y2, and I'm going to use the y in two places here. First, if y is more than 0, I return y. Otherwise, I return 0. So it means that, and I want it to return A. So actually, here I'm using y as int. And here I'm rating y as return type as A. So suddenly y is actually is ambiguous too here. So you have this situation, it's not just the subject and the return type, it's actually everything that comes from the environment that you should take care of. So actually that can mean quite a lot for the adaptation on things that you would not expect to have any influence. So this is the first aspect. The second aspect is I said that propagation makes things okay, but actually simple syntactic propagation is rather weak. Take a simple example here. I just expand it with a let. Suppose that I have something in between to make it meaningful, but here it's a very simple example. So I say let air is equal my match, and return air. So suddenly here, well, for x I can still propagate. Let's say that I propagate just because it's just a variable. But for the return type, here it's a let, the let is polymorphic, etc. I have no easy way to propagate from the fact that air is used the result to the definition. So actually this one will not work. Okay. Well, you can have more clever algorithms to do the propagation that don't rely directly on the syntax like GACs outside in, but this is another approach. Okay. So where are I here? So what's happening? We've seen that the problem, the essential problem is that we have those ambiguities, and when something is ambiguous, we should refuse to give a result or require some resolution of the ambiguity. But actually, what is ambiguous? I gave this first example and said it's ambiguous. But why is it ambiguous? Because I could use the equation and make it another type. But let's look at this other example. Here I'm not returning 1, I'm returning 2. And, well, this is not a big deal of a difference, okay? And here this one, of course, is not ambiguous because the equation is only equal in, so it doesn't care about bool. So, distinctions, they are very similar, and why should there be a difference between the two? And, well, my intuition, now, our intuition is that actually the first example should not really be ambiguous. There are another definition of ambiguity, so such that for our first example on top here, f of the type alpha t to int will be not ambiguous, and the type alpha t to alpha will be rejected as introduced, as not directly acceptable. We need a definition, okay? And the answer, of course, is we have such a definition. It requires to introduce some new notions. Particularly, we need the notion of ambivalent type. And we already define ambiguity as leakage of an ambivalent type. So what is an ambivalent type? Ambivalent type is a type that we need, such that we need to use an equation inside the typing derivation. Okay? Let's take this example here. I'm forcing, I say that y is of type A here, I'm using y here, and I have this if then L force y to have the same type as 0. So here I'm saying that I'm using the equation A equal int to give a result. So I could both give the result int or A, but in both cases I need to use an equation. So actually, we will say that actually it's not int or A, it's A and int, the type of the result. The ambivalent type, A and int. And ambivalence is propagated to all connected occurrences, just like we do in inference, okay? But of course we want to stop it somewhere, to have some way to resolve ambiguities, so we say that type annotations stop its propagation, they act as a wall. Okay, when we know that something has a type, we don't have to connect both sides. And then an ambivalent type is leaked if it occurs outside the scope of its equation, then it becomes ambiguous. And what happens is here, the typing rule for match leaves the result of our if construct outside as a result of the function, and it's outside the scope of our equation A equal int. So it's ambiguous. Okay, so that's the reason why we will deem this program ambiguous. Well, the basic derivation in front of this program will be ambiguous. Okay, so the consequence of switching to this new definition is that actually the first example before, the F example, no, is no longer ambiguous because if we don't use any equation, the only result we can result type we can give for this function is int. Okay? So if you use the equation, the result will be ambiguous. So we will be rejecting it as reject the derivation as ambiguous. So the only remaining one actually returns int. So it's possible. Okay. So of course we have also some ambiguous program. What do we do about them? The idea is this was all about leakage, and leaks can be fixed by anywhere we want, inner or outer annotations. For instance, here I just need to have both y and 0 of the same type. So if I say that 0 is of type A, there's no longer any ambiguity. Okay, this is I've chosen A as a type, and everybody can have type A here, and I'm using no equation outside of this annotation, and this works. Okay, so this is for annotation of expression. I could have put, of course, my annotation of the result type function is with therefore too. The variable is used with ambivalent types. We can also annotate its binding occurrence to prevent leaks, so in the opposite direction. Here I say that y as type A, and this is then I can use y both as type in and as the result, because these are considered two independent types. Okay. So of course, what you're interested in is the connection between ambiguity and principality. Somehow in the first slide, actually, I defined that ambiguity as the opposite of principality. This might be the way you were seeing it, but actually the new notion of ambiguity defined doesn't work at the same level, because here we're defining ambiguity as a decidable property of our typing derivations. That is, the derivation contains an ambiguous type or not. Whereas principality is a property of programs. Actually, when I have a set of derivation, is there a principal one in that set? And our approach is going to be to reject ambiguous derivations. And we have a conjecture, we are quite convinced of that, that the remaining derivations, once we have rejected the ambiguous one, if there remains some derivation, then they contain the principal one this time. And our strategy for type inference is that type inference is going to build the most general and least ambivalent derivation. And it fails if it becomes ambiguous. So now I'm going on to the so advantages, of course, compared to explicit type is that non-ambiguous types don't need annotations. So we accept more programs outright. We have less pressure for clever propagation algorithm. We can choose our algorithm. Actually, the idea is quite independent of propagation. It's just about deciding what is ambiguous. And it's particularly useful if there are many local definitions, if you don't want to put too many type annotations. And compared to using a type normalization like we did last year, inferred types are more predictable. Of course, that type normalization would be the notion of principality in that normalization would be strange. And also that we had a problem that we had a problem of compatibility with GADTs and between GADTs and object and polymorphic variants. And actually, leakage of ambivalent types precisely captures incompatible sharing, which was the cause of the problem. So now we can also use GADTs with objects and variants too. Okay? Yeah.
Do you have a uniqueness property?
Yeah.
Do you have a uniqueness property? You didn't say.
So I suppose this is what you would having the principal derivation. It's not enough for you.
Okay, so most general and least ambivalent means it's unique.
The most general and least ambivalent is going to be unique. Okay, so I go on to the comparison with outside-in this time, state of the art. Okay, outside is powerful constraint-based type inference algorithm where information is not allowed to leak from GADT case. Well, this is what it means. So all type information is going to go from the outside to the inside. Basic concept. The problem of doing a parallelism, of course, is the comparison very difficult because GSC7 implements a relaxed version of outside-in. Not really the one you have in the paper. And outside is essentially a constraint propagation strategy. In that meaning, it's somehow orthogonal to ambiguity detection, which is something about derivations. On the other side, OCaml also is not just ambiguity detection combined with some form of propagation, which relies on polymorphism, but is closer to what you will see as just syntactic propagation. We will give example of comparing OCaml 4 and GHT 7 because it's easier to compare a running system than just theory. Looks like I don't want to compare. Okay. So comparison on both sides. First example, OCaml fails while GHT 7 succeeds. Here, this is the example with the let expression. And here, so we don't have enough propagation. We first infer here that R as type int, but then later we realize that we are using R in a situation when it's at type A, but we are already outside of the pattern matching, so it doesn't work. Okay. Insufficient propagation. Other side, here, the strategy of outside in is that information should not leak from inside a GADT pattern matching. So if you do something like that, like you're doing the same kind of pattern matching, here I choose true because one is overloading in Haskell, so it's complicated. So here I'm returning true, but actually I'm not using the Z here. And so there's no way to infer from the outside what the type of Z should be. Okay? You could have the same situation if you use show Z, for instance. So you would just have a type class constraint, but not a concrete type. And what it ends up seeing, actually same kind of problem. That's actually for Z, it just infers some polymorphic type. And inside, it should be actually a bool, and it's not allowed to do unification between the two. Okay. And actually, we could say that outside in is very strong. As some small limitation, why we can say that outside in is very strong, it does something that we cannot imagine how to do. For instance, you can, in some situations, you can actually type some real GADT programs with no annotations at all. Because here what's happening is that I'm defining two constructors. And so R2 is just a normal constructor, A to R of A. And R1 is our GP constructor. As in the other example. So here, in case R1, I'm returning an int. In case R2, I'm returning the parameter. What's going to happen? It's going actually to type check first the second case because there is no condition there. Infer this type, and then realize that using this type, it can infer the first case. Clever. A limitation is that to be allowed to propagate more from the outside to the inside, implicit let is not generalized. So, if you derive it, it means if you define just the identity and apply it until twice, actually it doesn't work because here it's not generalized. You can, of course, put some annotations. Okay. So if I get a more complete comparison, GADTs, GSC has got them for a long time, while GHT 7 is more recent. While OCaml is just 1 month old, the system. The type discipline so is rather different because so in OCaml we have this ambiguity detection, where GSC shows outside in and some constraint, no leakage constraint. It uses something more. I will show in the next slide. So the point, as a result of that, actually in OCaml we have still polymorphic let, and this is actually important for ML. So some tests show that you use polymorphic let all over the place in ML programs. While GST doesn't have it, and Perfectly doesn't for that. So the inference is rather different. So actually, ambiguity detection is not related about your inference algorithm. So it's just something you can plug into anything, and particularly it works very well with unification inference like we have in OCaml. While outside it really needs some constraint-based inference. Principality, we think we have it, but we have no percentage. Maybe here GST clearly it's not principal, and moreover, actually, it was supposed to only accept the information that are principal. It's true for outside in, it's not true for GHT. So there are some contracts. Other features you might want with GADTs, in OCaml we have exhaustive net check, and it can come handy. It's aware of GADTs, but GADT has much more support for dependent type programming, like type string, like type label functions. I cannot do the full comparison. And I think I must finish. So I had some examples of why GHC is actually not principal. The first example is just from the paper. I will not get in detail, but more surprising was this example actually. Suppose that I give, it's always the same function, but here I say that x has type TA and y has type A, and I pattern match on x, actually I do nothing on this pattern, I just return y. And for some reason, GHC infers this type. So apparently it's doing some kind of normalization. So for some reason y, it was y, but it returns int. And I have no explanation for why. And it's like I'm not going to explain it, but actually, so ambiguity indexation could actually be used without citing. There's no incompatibility, I think, conceptually. So, you must conclude? Okay, yeah. So, actually, just concluding remarks that we are still working on the formalization. We're quite advanced, but there are several possible approaches, either graph-based or set-based. The intuition is more set-based, but if you want to talk about inference, it's more about graphs. It's available in OCaml 4.0. You can see the details of it to use it in the language section of the manual. There are not so many examples available, but if you look in the repository, actually there are in the test suite. There are quite a number of examples. And it is a bit technical, but I will kindly ask you to test it with, if you use it, try principal, because this is the one that is supposed to do propagation correctly. While we have, of course, always ambiguity decision, which is required for some nest, but default propagation is probably not principal in any way for efficiency reasons.